Hello friends, I am Saroj Vishwas, gold medalist, first rank holder of 1994 batch in engineering stream of all the colleges affiliated to University of Mysore during that period. A BE in civil engineering from National Institute of Engineering Mysore, a MTech in structural engineering from Indian Institute of Technology, Delhi, that is IIT Delhi, a Sun certified Java programmer, Sun Microsystem USA. I have more than 25 years of professional experience in designing building structures and allied subsidiaries. I invite you all to learn with me how to design building structures using commercially available structural softwares with the help of some manual computation as and when needed. These sections we shall continue with primary load cases. In the primary load cases, we have already covered gravity load cases in the previous sections. So these sections we shall consider the seismic load. The seismic load that has to be applied in STAAD Pro model or any structural software is static seismic load or dynamics and dynamic seismic load. For STAAD Pro, there are certain parameters which has to be supplied for static seismic load. So we have to supply the zone factor, then response reduction factor, then importance factor, soil, rock or soil site factor, then type of structure, damping value, and period of structure in x direction and period of structure in z direction. Now, if we do not supply this period of structure in x direction and or z direction, STAAD will calculate by its own depending on the height of the structure. But we should not let STAAD to calculate this by own. The reason being that, for example, suppose consider the building shown on the sketch. Now, when STAAD will calculate the time period by its own, it will consider the highest point. So this is the highest point. So for STAAD, this will be the highest point. But actually, to calculate the time period, we should consider up to the eve height of this structure. So the time period calculated by STAAD will be a grossly wrong value. So that is why we should calculate the time period of our own and supply it to STAAD Pro. Next, we should come to the values that has to be supplied to STAAD Pro for dynamic analysis. This kind of command is generated by STAAD Pro when we supply inputs for dynamic analysis. So spectrum, then this is called method. CQC method has been specified by the code. There are other method, square root method, then absolute value method. X indicate the direction in which this dynamic analysis will be carried out depending upon the response spectrum PR we supply. Z045 is the magnitude of seismic force that is to be developed, that is to be generated in x direction. So 05 comes from Z by 2 I by R. So our project is in Delhi NCR, so Z will be 0.24. By 2. This structure will not accommodate more than 200%, so I you can take as 1. And response reduction factor, this structure has both concentric bracing in Z direction and movement frame in X direction. So for ordinary brace frame, the response reduction factor specified by the code is 4, whereas for moment resisting frame, the response reduction factor specified by the code is 3. will take the more critical one, that is 3. So this works out to be 0.045. Then this scale, uh, we have to change after both dynamic analysis and static analysis has been carried out. Finding out the base shear generated from the static analysis, we have to scale it, and both the dynamic analysis we have to scale. We may have to scale this value to match the base shear calculated by dynamic analysis to the value that has been calculated by static analysis. Then this is damping. Damping is 0.05 means 5% damping. MIS 0 means we may ask STAAD to calculate mass contribution up to certain mode. Suppose we ask STAAD to calculate mass contribution up to mode 3. So STAAD will, for the missing mass for higher modes, STAAD will calculate some value. So that will based on 0, and that will be based on 0 period acceleration when we say MIS is equal to 0. Now, when a building is subjected to a seismic occurrence, it vibrates under various modes. So, for example, it could vibrate. Suppose our structure is like this. Then it could vibrate like this. Could be the first mode of vibration. This could be the second mode of vibration. And this could be the third mode of vibration. So for each of these mode of vibration, there will be certain mass that will participate in generation of seismic load, that is lateral load. But that structure actually vibrates as a resultant of this various mode. So for simplicity, this actual vibration is resolved into this kind of components. So if we ask STAAD to calculate the mass contribution up to mode 3, so what happens to the masses which contributes on higher modes? So a static value is calculated by the software to add to the mass contribution for this first 3 node. So this static value is calculated based on 0 period acceleration when we supply MIS is equal to 0. Next come what percentage of load from the structure shall be taken by the software to calculate the seismic weight of the building. Usually for a building structure, either IS 1993 part or part 4 is taken. Part 4 is for industrial building and part 1 is for general building. Now for industrial building, the time period is taken based on eigenvalue or ridge vector. That is, the time period is taken from dynamic analysis, and which because of that the seismic base shear generated could be much lesser than a general building, because industrial structure is mostly a bare type of frame. There is not much of walls or any other kind of thing. They are only cladded with some metal sheet, or they could be open structure with having roof. But for general structure, it could have lots of wall and other fittings with them. So for this building, we have a office area, so we will consider part 1. So importance factor is depends on the type of occupancy that has been specified by the code. The response reduction factor is something by which we reduce the actual earthquake. So response reduction factor basically depends on what kind of lateral load resisting frame we are taking for a structure. It could be a moment resisting frame, it could be a concentric base frame, it it could be eccentric base frame, might have been especially detailed for seismic resistance, or it might not have been detailed for seismic resistance. So as the response reduction factor depends on this. So we do not design the structure for actual seismic load. We actually reduce this actual seismic load by response reduction factor. So this is something which explain why we reduce. There will be some overstrength in the structure, then there will be some strength. The structure will have capacity for energy dissipation due to its ductility, because structure doesn't fail until lots of hinges are created within the structures to create instability. So actual seismic load shall be this up to this part, but in actual design we reduce this by response reduction factor, dividing it by response reduction factor to make the design economically feasible. Now next come the time period formula. We have for this structure we have both moment resisting frame and both concentric base frame. For moment resisting frame, the time period formula given by code is the first one. For other type of structure, the time period formula given is 0.09 h by root d. Now for our structure we have both. In x direction we have moment resisting frame, in z direction we have concentric base frame. So in x direction we should consider this formula, in z direction we should consider this formula. But generally the second formula, that is this one, has its inherent demerit, because we might have a structure of this form and it could have only one base here, and we might have another structure, same structure. Now this could have a concentric basing of this sort. Now it cannot be possible that both of these structure have same time period in this direction. So many of the structural engineer consider the first formula, that is T is equal to 0.085 h to the power 0.75 for the calculation of time period. For our structure, the floor to floor height is 3.25. Then we might have to consider a plinth height. So assuming plinth height, the eve height is computed at 6.95 meter. So the time period works out to be 0.36 seconds. Now let us come to actual application of seismic load to the STAAD Pro model. We shall first define the reference load. Reference load will help the software to generate the seismic load. We shall define the cutoff mode shape, static seismic load efficient, percentage of imposed load. Now we have come back to the STAAD Pro model again. Let us Let us open the command STAAD Pro editor again. So let us scroll down to load case 11 in the template where we had defined the gravity load. Copy this load after self weight, all the loads after self weight. Scroll up to find the reference load R1, that is dead floor load. Paste it here. So as we had already discussed, there is no meaning of sign for dynamic analysis. So we shall reduce this. We shall remove this sign. This is what is recommended for analysis with STAAD Pro. So we need this reference load in all the three directions for dynamic analysis. Obviously, for static analysis, only global y direction shall be sufficient, but we are doing a dynamic analysis as well. So we should. So let us copy this load 2 times below. Control C. 1. So change the first one, GX, 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 GX. GOE is already there, so we do not need to change. Then Z direction. Note that while we paste this, we have to be very careful so that there is no change the typographical mistake. So in case when we save this STAAD editor and go back and start issue some warnings, so we should actually look for if there has been some typographical mistake rather than crawling here and there to look for what is the reason why STAAD is issuing error or warning message. So next reference load is wall load. So we have already defined wall load under load number 12. So let us go back to load number 12, member load. Copy this load. This is also a dead load. Remove the signs. Copy it again. Press it 2 times below. Again, provide it for all 3 directions. Next one is reference load R3, which is live load more than 3 kN per meter square. We have live load more than 3 kN per square for staircase as well as the mezzanine floor. So let us go to the load number 14, which is for live load. So let us copy the mezzanine live load and the staircase load. We are not copying this live load at the roof level, this 1.5 and 3, because code do not require this live load at roof or terrace to be considered in computation of seismic weight. So let us copy it. Change the sign. Paste it twice below. GX, Geo is shall remain as it is. Then GZ, then comes load R4 mass title LL up to 3 kN per square meter. We do not have any LL up to 3 kN per square meter or below that. So this is the definition of reference load. Then as of now we are defining a cutoff mode shape of 9. We might have to increase it later when we see the results of dynamic analysis. We have to, as per code, we have to see that at least that much of mode is considered in the analysis, so that total mass contribution is 90%. Then comes the definition of static load. Zone factor 0.24, response reduction factor 3, I is equal to 1. These all factor we have to take. We have to provide this time period in PX direction and PZ direction. That this is already has been provided. If it has not been provided, we have to change it. We already calculated the time period as 0.36, 0.33. So we should, if it is a different time period, then we have to change it to the 0.36. 0.36. And then R1 is the dead load, float dead load that has already been taken. Then we have to define R2. R2 is wall load. This is also dead load. 100% will be taken. Then R3 is live load more than 3 kN. So code specify that has to be taken. 50% of that has to be taken for seismic load computation. So let us 0.5. Then R4 load less than or up to 3 kN. We have to take 25% of that as per code. So let us write 0.25. Obviously for our case we do not have any load that is equal to or less than 3 kN per meter. Now how do we calculate this pair? See, this is the graph. This is the graph given in code for response spectrum. The formula for this is also given. This is for X and Z direction. This is for vertical direction. So we can calculate the pair for time period 0.5 second, 1 plus 15t SA by G. So if we multiply SA by G by G, we get 17.168. These are the value for medium soil. For other type of soil also we calculate these pairs similarly, and we can supply it to the STAAD Pro input file. You may see for load case 5, 6, the time period pair is as per the graph. It's start changing after certain time period. But whereas in vertical direction, it's remain constant after the starting point. So this is the way it has been defined in the code. For code hasn't given any SA by G curve for vertical direction. It has given it to the formula given in the code is similar to this. Whereas in x and direction, the h is given something like this: z by 2, I by r, SA by G. But for the vertical direction, that is y direction for STAAD, it has been given as h is equal to z by 2, I by r, 2.5, and it has been multiplied with a prefix of 2 by 3. So the SA by G value has not been given in vertical direction, it is 2.5. That is why the time period versus acceleration pair remain constant after the starting value in vertical direction. That is why it remains constant 24.525, 24.525, 24.525 in Z direction. The load case 8 and 9 we shall not scale. These load cases we shall use it for generation in the combination of serviceability load case, because code doesn't require the displacement estimate to be scaled up. So let us now save the STAAD Pro input editor. Now let us give a run to the STAAD Pro software so that we know everything is okay after we have defined the seismic load definitions and provided the record input to the STAAD file. So run analysis. Do you want to run with empty load? Yes, we still have empty load cases, that is wind load cases. We are yet to have defined it. So it has run without any warnings. You can see there is no warnings. There is no warnings. So our load definition of seismic load definition is okay. So with this, we come to the end of the section of the definition and application of seismic load. In next section, we shall define and apply the wind load cases. Till then, bye bye and see you.